So in the last couple of lectures, you've heard about approximation algorithms, and we emphasized what the gold standard for algorithms is. That is, we want an algorithm that's provably correct. It always does the right thing, deterministic, and most important, that its worst case running time is bounded by a polynomial function of the input size. And we've talked about in those lectures, or I talked on one lecture, and then Rob, who was here on Friday, talked about it, that we don't always have that. Those kind of algorithms aren't always available, and therefore we look for algorithms that achieve some, but not all of those three properties. And particularly algorithms that give up on absolute correctness, but achieve bounded approximations. You can calibrate and guarantee how much they diverge from the optimal solution. Okay, so today I want to talk a little bit more about sort of the underpinnings of that, of why that approximation algorithms are important, by starting on a topic called NP and NP completeness. And as I mentioned before, usually we do this topic before we do approximations, but in order to not break up the topic, we did approximations first, because I was going to be gone one day. So this whole area is really concerned, well, it's concerned with many things, but today what I'm going to be talking about is what's the notion of, we're trying to make precise the notion of one problem being more difficult than another, one problem being the same level of difficulty, one problem being at least as hard as another problem, up to the level of a polynomial-time algorithm. So this is going to start out somewhat abstract, and then we'll get to specific examples in a minute. So X and Y are different problems. So you can think of X as any problem and Y any problem that you like. For example, we've looked at a problem called, well, last time Rob talked about vertex cover, so you can think of, let's say, X as the vertex cover problem, and Y, in one of your homework questions, you looked at independent set restricted to a tree, but we can also talk about independent set problem on an arbitrary graph. Or you want to talk about X, any particular problem you like, but those two we'll get back to in particular. So we have these two arbitrary problems, and I don't mean instances of problems. This is vertex cover, not just a specific graph where you look at the vertex cover problem, but problem X, we say that Y is reducible to X. So this little symbol here expands to is reducible in polynomial time. So Y is reducible to X, and what that means, that's if and only if, this is going to get messy, an arbitrary instance of Y can be solved. So you can take any arbitrary instance of Y, and one way of solving it is to use a polynomial-time. It can be solved by a polynomial number of regular computational steps just kind of things we're familiar with in our algorithms, comparing two numbers or moving a number from one memory location to another memory location, etc. It can be solved by a polynomial number of regular computational steps. And when I say here a polynomial number, that's shorthand. polynomial number really for a number which is bounded by a polynomial function of the input size. Just as when we talk about an algorithm's running time being polynomial, what we mean is that its running time is bounded by a function that's a polynomial function as a function of the input size. Okay? So if and only if any arbitrary instance of y, problem y, can be solved by using a polynomial number of regular computational steps, plus, and this is the new ingredient, plus a polynomial number of calls to a black box, something that we don't detail, a black box that solves instances of x. So the way you solve y is by doing some amount of work that's normal. The way you solve an instance of y, you do some amount of work that's normal and regular kind of algorithm, but you're able to make calls to some unknown mechanism, a black box, that can solve instances of problem x. Okay? And how many calls are you permitted to make? You're permitted to make a number of calls that's bounded by a polynomial function, polynomial in the input size of y. Okay? So you've got this special power or ability to call this black box, and it can do its work, well, essentially by magic. But we're not counting for the time it takes for that box to solve instances of x. Okay, all we're counting is the number of times we ask it. So sometimes this black box is called an oracle because an oracle has that kind of magical ability to give you an answer without doing any great work. Okay. Now, this is pretty abstract. Okay, how many people think you got it? This is concrete enough for you? Okay, one. All right, good. You've seen this movie before, right? Maybe. Okay, so this is pretty abstract. Let me try to make this concrete with the following example. So here's an example. X is going to be the independent set problem. Okay? And what's independent set? Independent set is you're given a graph. So you're given some graph G, and that's the vertex set and the edge set. Okay. A subset of vertices is independent if no two nodes in S are adjacent. Okay. Well, remember, in your homework question, you had a homework question that had to do with independent set on a tree. And you could solve that with a polynomial-time algorithm, a dynamic programming algorithm. Okay, but in general, if you have a general graph, then we don't have any nice algorithms that do that, that solve it. But what was the problem in the homework was maximum independent set. We wanted to find a largest independent set in a tree. And you can think of the same problem as largest independent set in a graph. And we'll simplify that in a minute. But just looking at this, let's say here and here, those are two nodes that form an independent set. Is there an independent set here of size 3? Anybody see one? I don't think so. So I think 2 is the largest independent set in this graph. Now, if we had another node out here, then we could put that in, and then we'd have 3. Okay. Now, so that's the maximum independent set problem. In the whole theory of NP and NP completeness, there's a simplification that isn't absolutely necessary, but it makes things a lot easier if we cast our problems as decision problems. That is, decision problem is a problem that has a yes or no answer. Okay? So the version of independent set that's used is given G, a subset S is independent. Well, that's the same. And so the subset, the independent set problem, the problem given G and a target K, so both of those come in as input, the graph and a particular target. Is there an independent set of size K? Okay? So in this graph, if, let's say, the target was 2, then the answer would be yes. There's an independent set of size 2. In fact, there's one of size 3. But if there's one of size 3, there's one of size 2. Whereas if K was equal to 4 here, then the answer would be no. There is no independent set here of size 4. Okay? So we're going to be dealing with problems that have a yes-no answer. Those are called decision problems. So X is one particular problem. Let's define Y is the vertex cover problem. And you remember this was discussed just last Friday. Vertex cover is the problem of given a graph. Well, let's take this graph. Given a graph, a subset of nodes is a vertex cover if every, let's call it a subset S, if every node in G is adjacent. All right, not node, every edge in G is adjacent to some node in S. Okay? And then the problem is given G and, again, a target, which we'll call K, is there a vertex cover of size K? Okay? Now, you can make both of these a little more suggestive by saying both these problems, given G and K, is there a vertex cover of size at most K? And here, is there an independent set of size at least K? That's usually the way it's framed, just to emphasize the fact that you want big independent sets and you want small vertex covers. But as I was saying earlier, if there's an independent set that's bigger than K, there's certainly one that's of size K. And if there's a vertex cover that's smaller than K, then there's one of size K, as long as K isn't bigger than the total number of nodes in the graph. Okay? All right, so this is, again, a problem that has a yes or no answer. And here, let's say K was, when we made K equal to 3 or smaller, the answer was yes. Okay? Let's make K equals 3 over here. Is the answer yes or no? Is there a vertex cover of size 3?
Yes.
Who said yes? Yeah, and
It's the top two, not the top, very top one, but the next top two.
Yeah.
And then the one right down from the right. Yeah.
Okay. Yeah, that's a vertex cover because every edge touches at least one of these nodes, and it's of size 3. Okay? There's also a vertex cover of size 4. Take that into it and so on. But vertex covers we're trying to make small generally. Independent sets we're trying to make large. Okay, now you might see a relationship between this vertex cover and this independent set. And what's the relationship that you see? Yeah.
All the nodes in one.
They're what?
All the nodes in one and one node in the other.
They're complements. Yeah, the set, if you think of this as a set of nodes, and this is a set of nodes, the set of nodes that are in the independent set and the set of nodes that are in the vertex cover are complements of each other. And in fact, let me write down a theorem. The book doesn't ever call anything a theorem, but it does have a number for this, which is 8.3. So this is all in Chapter 8, I guess. In G equals VE, a set S, a subset of vertices S, is an independent set if and only if V minus S, the complement of S, is a vertex cover. Okay? So this is a fact. It's easy to prove. You can prove it yourself or look up the proof in the book. It's a very simple little exercise. And we're seeing it, an example of it in this picture. And you can convince yourself with other examples, and again, as I said, you can actually prove this very simply, and the book does have a proof. Okay, very easy fact from graph theory. So independent sets and vertex covers are very closely related to each other. One is not so different of a concept as the other. Now that we know that, and we're talking here about this polynomial time reduction, we'll go back to this definition, and again thinking of y as the vertex cover problem and x as the independent set problem. Let's try to make this concrete. So we have to think of how can we solve an arbitrary instance of y. So y is vertex cover, and x is independent set. Any arbitrary instance of vertex cover can be solved by a polynomial number of regular computational steps plus a polynomial of number of calls to a black box that solves an instance of x, and x is independent set, right? Okay? So we want to show that vertex cover reduces in polynomial time to independent set, and in order to do that, we have to satisfy this definition. Okay, so we need to think about an arbitrary instance of vertex cover. Arbitrary instance of vertex cover. Well, what does it look like? So instance of vertex cover is a graph G and a target K. Okay, so you've got a graph and a target. And you can do something with this input, as long as it only requires a polynomial number of regular computational steps. Okay, so the algorithm has to be bound, its time bound has got to be bounded by a polynomial function of the input size. Okay, and it can make a polynomial number of calls to a black box that solves instances of independent set. So Can anybody think of what we ought to do here to do this this reduction, given that theorem that's over there that shows how close these two problems really are? Yeah.
Could we just ask, solve problem y for g and then satisfy g minus k?
Okay, you said problem y. Which is y?
The vertex cover problem. Or, sorry, the independent set problem. X.
Okay, so what we're going to do is you take this instance of g and k, and then you compute. Well, let me write out g is equal to VE. Okay? Then you compute k prime equals v minus k. Right? That's certainly something you can do in polynomial time, right? One trivial subtraction. Polynomial time as a function of the input size, which is the vertices and the edges, the description of that graph. So you do this little arithmetic, and then call the black box for independent set with input. Well, what's the instance of independent set that we're going to use? G. It's the same graph as before, and now target k prime. Right? And that black box returns either yes or no. Okay? It says there is an independent set in G of size k prime, or there isn't. Right? And so that's the call. And how do you use that call? You say if the return is yes, then output what? Yes or no?
Yes.
Yes. Output yes. And again, we're relying on that theorem. Output yes, else output no. Okay? So this is how vertex cover could be solved. Any instance of vertex cover can be solved if you have a black box that can solve instances of independent set. All right? Now the polynomial time, as I was saying, is involved in doing this subtraction or figuring out how many vertices you have. That takes polynomial time. Your input is a set of vertices represented in some way. You've got to figure out how many there are. That's certainly just polynomial time. Subtract k, make this call, and then you get the output. It's either yes or no, and then you have to look at it. Is it yes, then you output yes. If it's no, you output no. That takes polynomial time too. I mean, it's one constant operation, but that's certainly bounded by a polynomial function of the input size. And taken together, this is an algorithm for solving vertex cover if by some lucky happenstance you happen to have a black box that can solve instances of independent set. Okay? So this whole thing is an example of a polynomial time reduction. Vertex cover reduces in polynomial time to independent set. Now let me ask the following. Problem, is it true that independent set reduces in polynomial time to vertex cover? Okay, I see some people nodding yes. Anybody nodding no? Okay. Okay? And there are two possible reasons why this might be true, or maybe many more. It might be true that y reducing in polynomial time to x implies x reducing in polynomial time to y. Okay? You might just think, well, this is generally true. You can just reverse these. Okay? That's not true. Okay, so that's not the explanation for this one. But why is it true that an independent set reduces in polynomial time to vertex cover? Well, we want to go back to the definition. Here we have the definition, and here we have a particular reduction that went the other way. Vertex cover reduced to independent set. But the point is that by that theorem over there, vertex cover and independent set are so closely related. Essentially the same logic works. In fact, I suspect I can do this literally by literal global replacement. Okay? This is independent set, and compute that, then call the black box for vertex cover. Yeah, this works, right? Yeah. Okay, and this works as well, but it's because of that theorem over there. These two problems are so closely related that this same kind of argument with this global exchange of independent set and vertex cover, not very global because there's only one of each, but anyway, that gives you the proof for the fact that independent set reduces in polynomial time to vertex cover. Okay, I know this has been kind of abstract. You'll see more examples of reduction, and if you read the book, I'm following pretty much the book's exposition here, but just with additional exposure, hopefully, it'll become more concrete. Any questions on this? What it means to be what a polynomial time reduction? One problem reduces in polynomial time to another problem. Yeah.
Why is polynomial time reduction not generally reversible? Like, could you give us an example of a situation where one's reducible to the other, but it's not true in the converse?
I can certainly give you plenty of examples where that's true. The question is whether I can convince you that it's true for that particular instance. And I suspect, if I thought about it a little bit, that this being able to actually prove that it doesn't go the other way may be equivalent to the open problem that we're going to get to, the big open question. So this sounds like a great homework question. Whether, maybe we'll come back to that when I have thought about it a little bit. Okay, but yeah, just generally it's definitely not true that whenever we see this, we definitely know the other as well. Okay, now let's make some elementary uses of this notion of reduction. So the first one is, the book calls it 8.1. If problem y reduces in polynomial time to x, and x can be solved by a polynomial time algorithm, then what? So y can reduce in polynomial time to x. That's according to this definition of what it means. And now I'll put back the abstract. This is y and x. Y and x. And this was y. And this was x. So this is saying y and x have this relationship as given by this definition, and on top of that, x really can be solved in polynomial time. There's some polynomial time algorithm to solve x. X can be solved by an algorithm whose running time is bounded by a polynomial function of x input size. Okay? Then what can we conclude about our ability to solve y? Yeah. Yeah, then y can also be solved. Then y can be solved by a polytime algorithm. Okay? Well, just think of this definition here. The work that you're doing to do the reduction, both before you call the black box and after you've called it, is polynomial time. Here in this definition, we were just saying you call the black box a polynomial number of times, and we didn't count for how much time it took, how much time the black box takes. But now if we're saying if the black box actually inside of it is an algorithm that running time is bounded by a polynomial function of input size, then y can be solved. Then we can just put the two things together, and we have a completely constructive, explicit description of how to solve y by a whole mechanism that whose total running time is bounded by a polynomial function of input size of y. Okay. Now there's actually a little subtlety here, which has to do with the fact that a polynomial of a polynomial is still polynomial. Okay? So the polynomial work that you're doing in order to make the calls, let's say that's polynomial f of the input size of y. Okay? And then you're making some calls to a black box that solves x, and its running time is bounded by a polynomial function of its input size. Its input size is not necessarily this input size to problem y. It could be bigger. Okay? But how much bigger? Well, no bigger than the amount of time that was spent to set up the reduction. So if this, well, let me be completely concrete for you. Let's say I did cubic time to do the reduction, to set up the instances that are going to be fed into the black box for x. And let's say that the algorithm that can solve instances of x is a quadratic time algorithm. Okay? Every quadratic in its input size. So it's going to be quadratic in its input size, but its input size is certainly no bigger than the time that was taken to set up the instance. So we have y cubed squared, which is equal to y to the 6th, right? Not to the 9th. Yeah. And that's still a polynomial. Okay, so a polynomial of a polynomial is a polynomial. And if we make a polynomial number of calls, then that has to be factored in there as well. That'll be another exponent, but we still remain with a polynomial. Okay, if most of you didn't understand that fine point, that's okay. It'll dawn on you maybe at some point, but otherwise, this is the main conclusion, and you can kind of see this intuitively. I'm just saying there really is a technicality here when you think through the specifics of how this goes, the technicality of polynomial of a polynomial. That'll come up again in a minute. So this is our first conclusion, just really from the definition of what a polynomial time reduction is. And the second is the same as the first. So I'm not going to write I'm going to write the same statement, just in I think it's called contrapositive form. 8.2. Suppose y is reducible in polynomial time to x, and y cannot be solved polynomial time algorithm. So it's just a fact of nature, whether we know it or not, y cannot be solved by a polynomial time algorithm. But y is reducible to x in polynomial time. So we can conclude from this, then x cannot be solved in polynomial time. There's no polynomial time algorithm to solve x either. If there was none to solve, no polynomial time algorithm to solve y, and y can reduce in polynomial time to x, then x cannot be solved in polynomial time. These two are the same. Okay. These two say the same thing, just one is in the contrapositive form. And because you know, if I say P implies Q, that's the same thing as not Q implies not P. Okay? Those are the two equivalent statements, and that's all I've done here. Right. But this is the form that's usually, this is the form that's that's the most interesting, and it will be exploited in the whole theory of NP completeness, which I haven't even defined NP or NP completeness or any of this. We're just talking about reductions at this point. Okay. Everybody see this? These are two of the same. So if somehow we're able to establish that y just cannot be solved in polynomial time, and we can establish that y is polynomial time reducible to x, then we get that additional conclusion that x cannot be solved in polynomial time. And we can build up a whole series of these implications to, if we actually have a problem that we know for sure can't be solved in polynomial time, and we have all these polynomial time reductions, then we can build up a whole set of other problems which we can conclude cannot be solved in polynomial time. Okay, we're not quite going to do that, but we're going to do that in spirit. We're going to come close to that. Okay. Okay, I've said that the way we talk about this, this symbol is that y is polynomial time reducible to x. Okay, those are the words. There's other words that are used. So y polynomial time to x means that x is at least as hard to solve, at least with respect to polynomial time, as y. Okay? So this whole notion of reduction, at least in the context of algorithms, was it was started, I guess, in 1973. And how many years ago was that? 37? Okay, so I was around then and was actually my thesis advisor who formalized this whole business. And I never am comfortable with this statement here. I always have to stop and parse it. You know, for 37 years, it just has never sunk in to a point where that's natural. This is natural to say y is reducible to x. You know, although I would have liked it if they'd put the inequality the other way, but all right, I can live with that. But this one, x is at least as hard to solve as y. Okay, so you think of that, what does that really mean? Well, if we had a fast algorithm for x, we would have a fast algorithm for y. That's what this thing says. Okay. So if we don't have a fast algorithm for y, we can't have a fast algorithm for x. That's what this thing says. So if you're trying to get an efficient algorithm for x, you're going to have as much difficulty with getting a polynomial time algorithm for x as you will for a polynomial time algorithm for y. Okay, I mean, you can make this make sense if you stop and go through it and so on. I'm just saying that since the beginning of this whole theory, this statement has just never leapt out at me as, yeah, that's really what this all means. Okay, but you're welcome to say that if you want. Okay, this is the formal definition, and this is sort of the intuitive way that people talk about it. Okay, polynomial time reductions. Now, zillions of polynomial time reductions are known. At the beginning of this whole theory in 1973, people used to catalog them. There's a book that's full of many known polynomial time reductions. Then things were published and maintained in journals and then in websites, and finally there's just so many of them nobody pays attention unless they're extremely important. So lots of polynomial time reductions between problems of interest are floating around, and we're going to look at a few more of them. Very rarely are they as easy as the reduction, the mechanics as easy as the reduction of independent set and vertex cover. Those are two that are particularly close to each other, two problems that are very, very close to each other, and therefore that's good for teaching. Most of the time, for problems that are of interest, you have to work you have to work more to be able to show how there's a polynomial time reduction or why there's a polynomial time reduction. So let me show you another one. And this also introduces a problem that's been particularly central in this whole theory, the problem called satisfiability. And in that problem, the input is a Boolean formula. So a Boolean formula which has clauses made up of the ors of literals. And a literal is a variable that's either negated or not negated. Okay, variable negated or not. Okay, too many words. Oh, and then the clauses, Boolean formula made up of clauses, made up of ors of literals, and then the ands, the clauses are anded. Okay, boy, I'm sure everybody has seen Boolean formulas in one class or another. You may not have called them that, and you probably didn't make it as obscure sounding as what I've just done here. Well, let me just give you an example. x1 or x2, not, the bar over it is the negation sign, and x1 not or x3, and let's do one that has more than two variables, two literals, x1 or x2 or x3 not. Okay, so this Boolean formula has three clauses. They're connected by ands. This is the and sign. Inside of each clause you have literals. This one has two literals. This one has three literals. A literal is a variable, x1, either unnegated, this one is unnegated, or it's a variable x2 that is negated. Okay? so inside we have the literals are connected by ors, and then the clauses are connected by ands. This is a Boolean formula. Now this Boolean formula is satisfiable if and only if we can assign truth values to each variable, making the entire formula true. Okay? Now, if you paid attention carefully, you'll notice that I said you assign truth values to variables, not to literals. Because when you assign a truth value to a variable, let's say you make x1 true, that automatically makes x1 bar false. So, can we make this formula true? Well, if I make x1 true, that makes x1 bar false. If I make x3 false, that makes x3 bar true. Okay, and here's another x3 bar, that becomes true. And so this is an or in here, so all you need is one true to make that clause true. These are ands. You need each one of these clauses to be true. So this is true, and this is true. And so we see here a way of making this Boolean formula true. Okay? As an example of a Boolean formula that you cannot make true, okay, x1 and x1 bar. Rather trivial, but you cannot make this true. If you make x1 true, you're making x1 bar false. If you make x1 false, you're making x1 bar, well, you've made x1 bar false. Okay, so that's no good. All right, so this cannot be satisfied. Made true, and that means satisfied. Satisfied. Okay, so the satisfiability problem is the following problem. Given a Boolean formula, call it, well, give it a name, script f, can script f be made true? Can it be satisfied? So this is a yes-no problem, okay? And probably everybody has had a course, CS20 or some logical circuit design course or something, where you've seen an algorithm that actually solves the satisfiability problem. So who wants to propose an algorithm? Yes, Michael.
Check every combination of all the variables.
You check every combination of true and false assignments to the variables, okay? And that's formalized usually in something that's called a truth table, right? Okay, so you all know how to set up truth tables to then evaluate whether or not there's a combination of true and false assignments to the variables that makes the formula true. Okay, we'll think about later what's the time bound on that algorithm, whether that's a polynomial-time algorithm or not. But anyway, here we have a problem called satisfiability. 3SAT is another version of that. 3SAT is just a version of satisfiability where every clause has at most 3 literals. Okay, next time what I'm going to do is show you how the 3SAT problem can be reduced in polynomial time. So I'll just write it down. 3SAT reduces in polynomial time to independent set. So I want to show you that reduction just as a way of getting additional exposure to reductions. And then we'll also get into what NP is and NP completeness and all of that stuff. But the foundation of it all is to be comfortable with polynomial time reductions.